Our next speaker is a special invited talk. So he is like Bardienus Pieter Duisterhof. He's a graduating student from Carnegie Mellon University at the Robotics Institute. Okay, so before coming to CMU, he did his bachelor's and master's degree in aerospace engineering from Delft University of Technology, Netherlands. And currently, he is researching on reinforcement learning for tiny robots. The idea is to develop efficient AI for fully autonomous operation of resource-constrained miniature robots. So the work is in the intersection of computer vision, machine learning, and systems. And today, Bardienus is going to give a special invited talk on the topic of insect-inspired AI for gas source localization using a swarm of nanodrones.
Okay, thank you for inviting me today. My name is Bardienus Pieter, or as most people call me Bart. And today I'll be talking mostly about this project. It's called Sniffy Bug, in which we developed a fully autonomous swarm of tiny drones. So these are crazy fly drones, about 30 grams. And in this presentation, I'll also sort of briefly wrap up with two of my other more recent projects on tiny drones and flapping wing drone racing. So I'm excited to speak about this progress, and yeah, I'm curious to see what sort of questions you have towards the end of the presentation. So we'll start off with the gas seeking project. Gas source localization has many use cases, mostly in factories, as we figured out, as there's some sort of chemical leak somewhere in a complex factory, and it's important to find it quickly, not just because of economics, but it's also just unsafe to send people in there. So the people we talked to in the industry, they told us that essentially those people go in there with gas meters and trying to find a leak. So wouldn't it be great if we can find the gas leak using a swarm of tiny quadcopters, a swarm of tiny drones, and make sure that people don't get into danger. So that is the core idea of this project. So why is this hard? GSL, or gas source localization, has challenges that fall into mostly two categories, which is navigation and gas seeking. From a navigation perspective, is trying to make drones that are around the 30 grams, about 10 centimeters or 3 inches in size. Then navigation is hard because of the resource constraints, like pretty constrained sensors and unknown cloud environments. Gas seeking is also a surprisingly hard task. If you would compare this to something like a point source or radiation source, a gas source is much harder to find because it will be a local optima, it will be changing over time. And the sensor quality that is available on such a small scale is also very limited. So the sensors that you have to use are just going to be very noisy and biased. So in this work, we present a swarm of fully autonomous and collaborative gas-seeking nanoquadcopters. We enable them by a novel bug algorithm, which is essentially using a set of simple rules. But we evolve the parameters in our novel simulation platform. And then finally, this is our final contribution as a pipeline for end-to-end environment and generation and modeling gas dispersion that we call GDM. So for this part of the presentation, for the gas seeking part of the presentation, I'll talk about related work, methodology, results, and conclusion. I'll keep the pace up a little bit because of the relatively short time frame, but please feel free to ask questions afterwards or reach out to me after the talk for more information. So in related work, most algorithms fall into the bio-inspired, probabilistic multi-agent or learning-based category. For bio-inspired, what I mean is it's mostly mimicking biology. So they're trying to mimic a lobster or a silkworm moth. Probabilistic models try to use some prior of how gas leaks work and disperse through the environment. And then there's multi-agent and learning-based algorithms that more or less speak for themselves. So one key thing to take away from experiments in the previous state of the art is that the experiments are extremely limited because it's really hard to test the gas leaking robot. Gas could be dangerous. You need a pretty large room. It's just not very easy. So many times people resort to other options, like in this scenario where people would model a gas source and then use the gas source, or in this case, it's like a super small sort of gas chamber. So we thought, we need to make a step towards more realistic scenarios. We also want to make it easier to compare algorithms with the simulation platform. So this is another example of a test. So you need to consider that this drone is 10 centimeters in size. So that the area you just saw is very small, 0.8 times 2 meters. And the area that we'll be using later is 10 by 10 meters. So it's a bit bigger. The methodology can be split up in system design, simulation pipeline, and algorithm design. So first for the system, we use a bit crazy fly, and we equip it with sensors to be able to avoid obstacles. It needs to be capable of odometry, gas sensing, and relative ranging between different drones, as well as communicate with them. So the system that we developed is fully distributed. So there's no ground station active, and they're all estimating each other's relative poses by ultra wideband, which is essentially they're communicating each other's states in terms of mostly velocity and the rates of the different states, and with that they can determine the range towards each other in their own coordinate frame. And we later use that to collaborate. So for those familiar with the Bitcase Crazy Fly, this is just a simple multi-ranger deck. We have the flow deck, and then we have this deck that we developed ourselves with the gas sensor and ultra wide. The total weight comes down to 38 grams, roughly 38 grams. So for the simulation pipeline, there's two main steps that I'd like to talk about. First is auto GDM, auto gas dispersion modeling. So we basically generate the environment fully autonomously and model the gas concentrations. And then there's formulator, which is essentially using that information and using it to evolve agents in that environment. So for auto GDM, when we first started this project, we were kind of amazed that there was not yet a tool out there that could effortlessly generate a large number of environments, because we felt like it was really useful and important for research in this area overall. Like not everyone can be a CFD expert, so that's why we wanted to make something that's effortless and it allows for learning and benchmarking. So the environments need to be varying and it needs to be tunable parameters. The main building block that we used is a ROS package called GADEN. GADEN does multi-steps. So there's an environment generation using a CAD model. There's wind simulation using computational fluid dynamics, CFD. And there's gas dispersion modeling. Turns out that this part is not automated. So that's essentially what we did. Auto GDM is using GADEN for the filament simulation. But for the computational fluid dynamics part and the environment generation, we built our own pipelines. For random environment generation, we use a procedural environment generator. So essentially it has a number of tunable parameters like environment size and number of walls, number of rooms, these sort of things. And it outputs it to the occupancy map. So we use, so to say, 2.5D environments that are being generated. So we generate, as I said, we generate a CAD file, 2.5D, and we then use that CAD file as an input to the open source toolbox. It's called OpenFoam. And essentially you can just enter a CAD file and using a bunch of parameters that we also randomized, like what is the inlet and outlet conditions and the source condition or the source position. You can essentially get a flow fluid, like a wind field out of this computational fluid dynamics toolbox. For source placement, this is kind of an implementation detail, but we figured it's really important to decide where to place the source. If you place it somewhere where there's no wind, then essentially like it just becomes a point source, and the agents would learn something that's not necessarily relevant to the real world. So we end up placing it somewhat far away from the outlet where there's still some wind present. So it gets actually dispersed through the room. One other thing to note is that because we can randomize these environments in a random environment generator, and a wide variety of environments will come out. So this is like a super easy environment for the robot to find the gas source, whereas this is like reasonably hard to figure out where the gas source is, because this, in some experiments, this even had a higher concentration than the actual gas source. Finally, the last part of the simulation pipeline is Swarmulator. So it's a very fast C++ simulator that's 2.5D. The great thing about Swarmulator is mostly that it's fast, and you can very quickly train an agent. Like our final algorithms could learn parameters within a couple of hours pretty reliably. For the algorithm design, this so we have these systems of small drones, right, with relative range information, and we have laser rangers for obstacle avoidance. So these laser rangers are in 4 directions with 90 degrees in between them. So like left, right, front, back for the drone. And needs to be able to avoid obstacles and avoid other agents, and then hopefully collaborate in a meaningful way to find the source with the other agents. And we found that there's some swarm navigation work that uses simple rules on these tiny drones for navigation instead of a traditional SLAM pipeline. But we also found that there's some gas-seeking work using particle swarm optimization. And we figured that particle swarm optimization is a good starting point for our algorithm, and then we intended to use a set of rules instead of more complex, lighter algorithms. So our solution is SniffyBug. It's a big bug algorithm that uses a set of simple rules with evolved parameters. And it is a novel particle swarm optimization powered bug algorithm for Source Localization with evolved parameters. So we generate waypoints in each robot's reference frame with particle swarm optimization, and then we track them using a set of rules with evolved parameters. So the waypoint generation, it happens when it reaches within a certain distance from its previous waypoints, when it takes too long to find its previous waypoint, or when one of the members of the drone swarm sees the best seen position, that means that one of the agents sees a high gas reading that the entire swarm has never seen before, so it decides to reconsider its options, basically. But how do we get there is the question. But first, let's zoom a little bit more into waypoint generation. So this GIF, I think this GIF is super cool. This basically shows how particle swarm optimization works. And in our case, every particle will be a drone, and it's known to be very robust and to scale well to a larger number of agents. So this is kind of why we picked it for our purposes. We have 2 states where no gas is detected. Basically, what the drones, like in the real world, what you would see is in most of the environment, there's probably not gas to be detected because of the lack of sensitivity of the sensors. So at that point, we just explore. So we randomly travel in different directions. But once one of the agents has found gas, then we do a directed search with particle swarm optimization. For waypoint checking, I distinctly remember this part of this project where it sounded very easy to come up with a policy for using laser range to avoid obstacles. I thought we have all information. How hard can it be? But it turned out that it's actually pretty hard, because there's all these sort of edge cases that you need to take care of. So we needed to keep constant job because the relative range estimates with ultra-wideband seem to be more accurate when we did that. There's only 4 laser rangers, so there's a large blind spot. And we also need to avoid agents and obstacles simultaneously, so they can be trapped in the corner together, and it could be kind of messy. We came up with 3 states. I think it's easy if I show the figures while explaining it. So when there's no other obstacles or agents around, we do this thing that we call line following. So the drones travel in, this is the direction, these are the directions where the laser rangers are pointed. And as we need to keep yaw constant for the relative ranging system, we end up with this sort of zigzagging motion. So it's only moving in the direction of laser ranges, so it can see obstacles coming up. But it ends up being this sort of zigzagging motion to travel towards the waypoint. And then there's wall following. There's actually something seen in some insects. Instead of, like the more engineering focused solution would be to create a map of the environment and solve for a path towards the goal waypoint. Here, the more naive approach is to simply follow the wall towards the waypoint. So it seems like with a larger number of agents, eventually you'll discover complex structures as well. Attraction repulsion swarming. This is kind of this is a pretty well-known algorithm in robotic swarming. So essentially, what we do is we model a force, and this only is activated when there's other agents close and there's like obstacles like walls nearby, and then we model a force away from low laser range values, so away from obstacles. Then we model a force away from other agents. This seems to work somewhat well in making sure that you can like pass by another agent close to the wall, for instance. So then we do the evolutionary optimization with 13 variables. So this is essentially all the variables that are present in the algorithm, and we evolve them using the platform that we've built. So the cost that we created is just the average distance to source. So it forces them to not only not crash, but also forces them to travel efficiently towards the source. So it's the average distance over an entire run. And we also add a penalty for collision just to make them a bit more careful in the real world. And this is another like fun, like I'd almost say implementation issue or implementation detail. They're like with evolutionary optimization, if you have this wide variety of like heterogeneity in the distribution of environments, it's possible that the algorithm will learn to solve only the easy environments. So on average, it will do well on all these environments. Like we would evaluate 100 different environments, but it doesn't necessarily learn to solve this. So there's this strategy called doping, where you focus, like you present the algorithm more often in evaluations in evolution, in artificial evolution, with the harder environments. So each generation in artificial evolution, there's some probability that each environment is presented to the algorithm, and the probability is much higher for harder environments. So I think this is a very cool. It helped us a lot, actually. You should see if you get the results in the paper. So let's go to the results. This is I think this is the most exciting part. So we generated 100 randomly generated environments in a size of 10 by 10 meters, both in simulation and in real life. We use 3 agents. Definitely this algorithm could be scaled to more agents, but this is just makes it easier to actually do the experiment. So we started in simulation and compared different algorithms. So here we did evolve particle swarm we did evolve parameters of particle swarm optimization with doping. So this is essentially the version that I just presented. But we also compared it to some other strategies that we considered. So here's success rate, here's average distance to source, and here's average time to source. So essentially we compared it to a strategy where it would get the wind factor. We would give the algorithm the wind factor, and it could use that in its algorithm. And this strategy is a more naive chemotaxis, a more gradient seeking algorithm. The main thing to take away from this is that we considered different waypoint generation algorithms. We kept the obstacle avoidance strategy, the simple rules, we kept those the same. Then here you see, I think this is also very cool. You can see that doping, so this is evolution without doping, this is evolution with doping. And this sort of you could think of the cost of it's almost the cost of the evolution or of the population after evolution. And you can see that sort of doping takes care of this long tail. So it focuses more on this long tail because it has a higher cost. Now all of a sudden we have a distribution that's lower and overall performs better. So this is also quite interesting, I feel. So this is the parameters that we selected manually. Essentially, we figured that it makes sense to stay away from walls from a certain distance, and we tried different parameters in the real flight arena for some time, and then we compared it with the evolve parameters, and it seems like the evolve parameters have actually learned to perform better. So this is what it looks like to evaluate parameters like evolve parameters in simulation. So again, wide variety of environments, and they all seem to find peaks in gas concentration. One thing to consider is that in this case, it doesn't seem to find the actual source, but that's also not super surprising considering that this peak was actually higher, like more gas was here than at the source. Just so shows how hard gas source localization is. Now the real exciting part, when we took this to the flight arena, we set up some different environments, and we had a can with actual alcohol with a fan that would disperse it through the environment. And the question is, does it actually work in the real world? And to this point, it wasn't really certain. There have been some papers that have studied this, but not all of them were as conclusive. So we weren't really sure how well this would work. So let's go to the experiments. This is our flight arena at TSL. So the gas source in this environment was here. So it actually, in this case, the gas source is here. One of the constraints in this kind of testing is that the battery life of these systems is somewhat limited. So you'll see the drone drops down, just has a somewhat more degraded battery. But you'll see in the easier the environments are, of course, the easier it is to find the gas source. So again, the source is here in the back. You see the small dots. It's almost hard to see on your screen, I must think. But in most cases, it will converge towards the source. So in this case, as you can see, the drones are here, and the gas is here. So essentially, it shows that it can find the source. We also show that this is on the y-axis. You'll see the amount of gas detected, more or less. And you'll see that the evolve parameters detect more gas on average, so they actually do perform better in the real world. So this sort of, in a way, validates our simulation pipeline. I'm going to skip this in the interest of time. This is what I just said. And just to summarize this work, we contribute the first fully automated gas dispersion modeling pipeline, and I've shown that it can be used to some extent evolve algorithms to perform well in the real world. We evolved a novel computationally efficient bug algorithm using a set of simple rules. It's just to be capable of gas source localization and navigation and avoidance in collaboration with other agents. And with that, we contributed the first fully autonomous swarm of gas seeking nanoplatforms. So now there's two more projects that I would like to briefly talk about. I think those are really fun projects that we could briefly go over. So the previous project was my master thesis work at TU Delft. This project that I'm about to present is was some sort of research internship 2 years ago, where we also used a tiny drone, but now for light seeking using a deep reinforcement learning policy. Again, we use a BitCage Casify. This time we have a light sensor on the multi-ranger there. So essentially this version of the Casify is a lot lighter than, 5 grams lighter than the gas seeking version. And the main challenge here was, or the main interest here was to see if we could fit a small deep reinforcement learning policy onto the system. Considering that it only has 196 kilobytes of RAM, it seemed like it's quite challenged. So we started with the simulation environment, something called Air Learning, which is essentially AirSim, Microsoft AirSim, which uses Unreal with a deep reinforcement learning backend. And then we randomize the source position and we model the source as a line quoted source, and we see if we can find a policy that can both avoid obstacles using the same laser ranges as we used in the last project, but it can also find the light source by essentially deciding to move forward left or right with the policy. The inference implementation is one of the favorite parts to talk about for me, because I don't think many people think about it. We use TensorFlow Lite and UTensor. TensorFlow Lite seemed like it wasn't fast enough. We were able to use TensorFlow Lite on this thing with about 3 hertz of inference speed. And then UTensor seemed to have a small memory leak. But, if there's a memory leak of just 1 kilobyte in each inference step, then if you only have about 33 kilobytes of RAM available, then you very quickly run out of memory. So we ended up implementing our own library, which wasn't that bad because our policy was relatively simple. But it was something that came up that I thought was interesting to share. For flight tests, we used this slightly smaller arena, 5 by 5 meters. But we made it pretty complex with all the obstacles we used. So these poles that you see here, they made the life of the drone pretty difficult. We collected a large number of experiments, and we showed that essentially they've learned to fight to avoid the source, or not to avoid the source, to find the source with good accuracy. So this is essentially a random walker in the same environment, and the success rate is reaching within I think a meter of the source. So you can see that the learning policy definitely does better than the baseline. A quick demo. This is not the real speed. The final speed we used for the paper experiments was 1 meter per second. But this is so that we can actually like walk with the drone and show what it's doing. This is the actual speed, which is like the final trajectory of one of the runs. So if you want to know more about this specific project, the paper is online, and yeah, let's go on to the final project. So most of the work on drones is on quadcopters these days, but a very interesting line of work I think is flapping wing drones, inspired by nature to some extent. The advantages include that they're more safe, and I think that's the biggest advantage, because those wings are just very dangerous, and they're very interesting platforms. So for this project, we used the Delphi Nimble, which is a research platform developed at GDM, and we participated in a drone race. So essentially, what we needed to do is avoid obstacles, fly through a window, fly through some hoops, and to do all of that with just one single camera with a small microcontroller on board. So we ended up doing line following, where you basically just use a color filter and fitted a bunch of lines to a function, and then ended up taking the derivative to follow the line. We were able to follow this line in the picture, and then we also detected circles with a half detector, and we're able to fly through very small circles with the same drone. So this is the half detector. You can see it in this image. Let's see. In the interest of time, I'll try and show a quick demo, and then I think it's time to wrap up the presentation. So this was some very coarse line following with the flapping wing, and we had do the same thing at the competition, the IMF competition. And we also had this the window, or the hoop drive fly through. So you can see it here. I hope it's visible on your side of the connection. But, yeah. So yeah, I wanted to highlight that drone racing is a lot of fun for anyone considering doing it. We had a great experience traveling together and hacking this together more or less. And yeah, that marks the end of our presentation. I'm looking forward to any questions you may have.
Thank you, Bart, for such interesting projects that you have discussed. And now I would request if there is any question from audience. You can.
Hello.
Yeah.
But I'm having a question regarding to what kind of controller you have used in this particular drone.
Are you talking about the quadcopter drones? So the gas project essentially?
Yeah.
So it uses simple PID controllers, and it has two levels of PID. So it first has a rate loop, and then it has an angle loop. And like in addition, we also use the velocity loop. So like in total, you would have 3 different PID loops that are nested. Basically, does that answer your question?
So this algorithm is being implemented into the PID control system loop.
Yes, the algorithm that you see on this slide, the output of it is basically a velocity command. So it's move X meter per second forward or left or right, and that command is being tracked by different layers of PID controllers.
Okay. And for processing part, what kind of hardware you have used?
It's all on board. It's a Cortex M4, and it's really constrained. And so yeah, these are the specs. So it's like this. The drone is basically a flying PCB, and on the lower side it has an MCU, a Cortex M4.
Okay, and and this you have also used the cameras for vision based sensing is also you have implemented.
Not on the quadcopters, but we have implemented it on this flapping drone.
Okay.
So here on this flapping drone, you see a tiny camera here, and this camera has a camera facing forward. There's a microcontroller on the back that it uses for processing, and yeah. But for the crazy flies, it's a work in progress, I would say.
And for quadcopters, you what kind of sensors you have used?
Yeah, I'm sorry. This is. I feel like half an hour was short. It's hard to cover everything thoroughly. So my PC is freezing, but I can talk you through it. It should be it. Yeah. So for the quad rotor, we have state estimation with an object flow deck. So in this picture, that's number 4. What it measures is object flow for some state estimate, so that you can like hover in place and use that for control, for velocity commands. We have these, like you can see these lasers here, number 3, and they're used for obstacle detection and avoidance. Did that answer your question?
Yeah. Okay. Thank you for your nice presentation. Thank you very much.
Yeah, thank you for attending. I understand it's 7 p.m. where you're at. Is that correct?
It would have been very better if your sound is not up to the mark. So we would have enjoyed a lot. But somehow it's a very impressive presentation still.
Okay. Also, the sound of that doesn't come through somehow.
Yeah.
Or doesn't. Okay. Yeah.
So.
Okay. Yeah.
Okay. Thank you. I mean, any more questions from audience?
Hello, Bart. I have one question. Can you hear me?
Yes, I can hear you.
But you have used that multiple drones, and every drone you have treated as you have used the particle swarm optimization to reach your desired goal to manage all these drones. So my question is that it means in real time that because this kind of evolutionary algorithm takes a lot of time for the calculation. So how you manage this calculation part in distributed role system?
Thank you for your question. So the evolutionary optimization means that, for instance, in particle swarm optimization, there's different weights to the different components. And it's kind of a design problem that almost by definition, as a human, you would solve in a non-optimal way. And so all the evolutionary optimization is offline. So we take the algorithm in an offline simulator, and we find the single best parameters for instance, particle swarm optimization. And we do the same thing for something like at what distance do we need to start avoiding a wall? So at what distance, like the laser ranger detects, do we need to start avoiding the wall? And the goal of that is to, like, we have shown that we can also make this work without all the evolution. But we have shown that by optimizing those parameters offline, the thing works better. So there's no online evolutionary optimization. That would indeed be, that would not run in real time.
Okay. Okay. Thank you, Bart. It was a very nice presentation. Yeah, that's a good one.
Thank you.
Yeah. So, Bart, I have one question. So, regarding that flapping wing drone that you have shown as a part of like the race thing. So, I'm just interested to know what is the endurance of that system, like how long it can fly. Normal design.
Yeah. So there's different, there's different versions. This version is kind of like a, I would say, research version that maybe has at most 10 minutes. But there's now a commercialized version that is available. It's called Flapper Drone. Like, so the postdoc that the scientist that developed this system has a spin-off where he develops the same system for commercial use, and that has an endurance of 20 minutes. So yeah, it just needs more R&D basically, and more money, I think. So yeah.
So any more questions from audience? So thank you, Bart, for that, once again, for that interesting projects that you have presented.